let me start from this. I want to. I've published a paper, my last paper, short ago. It's a physical review letters. We physicists, when we publish a physical review letters, are happy and proud because it's a sort of the best journal in the field, and it's a article on an experiment. It's an actual detector, a proposal of a detector for detecting a certain thing which has not been detected yet. So I want to get there. I will take you there slowly, and that will be the arrival point at the end. I'm not anticipating what is detecting, and I want to take you there through a voyage, a trip, which is quite also a trip in time, a trip through time, a jump in time. You'll see exactly what I'm talking about. So I will ask you to follow me into a trip, and I will be very careful in saying what I will talk about various parts of physics. What is established physics? What is physics we know? What is physics that we don't know? We're suspecting, we're exploring, and what is completely unclear? What is completely open now? And I want to try to be very careful distinguishing these things because I complain that often theoretical physics today mixes up a little bit too much and confuses what we know with speculations and things which are, people would like to be so, but are not so. So before starting the trip, let me just take 2 or 3 minutes for making clear what we know about the universe today in physics. And by physics here, I mean only what is called physical sort of fundamental theory. So not physical applications, not physical of complex systems, that this idea that in physics you might have a sort of bottom physical level which underpins all phenomena in reality. So what we know, even if people talk, including me, about much more than that, but what we know is only 3 things. We know quantum mechanics, we know general relativity, and we know the standard model. These are the only thing we know in basic physics today. And then, of course, the applications of this.
You're getting a lot of nods from the audience. They agree. They agree so far.
Yes, so far so good. Now, quantum mechanics, of course, it's not conceptually clear. People look at them from different perspectives. Nobody has totally clear ideas, but it's worked fantastically. As far as we know, so far it has always proven correct, even when people did not expect it to go correct. It turned out to be correct. More or less, it was written just in 1 year, in 1925. The full form of quantum mechanics is already in a paper of Max Born, Jordan, and Heisenberg in 1925. But then, of course, it had taken forever to put the mathematics to understand what was the physics, to understand the implications. We're still unraveling what is in quantum mechanics and, of course, incredible applications. General relativity also, it's all entirely in a paper in 1917 by Einstein. Its basic theory is there. He had the first version in 15 without the correct equation, and then 17 paper. And it's also a spectacularly simple theory like quantum mechanics. Quantum mechanics, if you want, it can be said by saying it's a single equation, xp minus px equal I. And then the rest follow in some sense. It almost takes a lot of work to follow. And general relativity, it's a single equation, essentially, the Einstein equations. But it has taken a century to see what is inside. And of course, all sorts of marvels which are predicted by these equations, like gravitational waves, black holes, expansion of the universe. Nobody believed them, including Einstein. But then it has turned out clear and true. And general relativity, unlike quantum mechanics, is conceptually clear. It takes a lot to digest it. People were long confused, including the physicists. But there's no mystery of what it says about the world. And the third thing we know is the standard model. Standard model is sort of not as clean as the other. It's a patchwork of things. It has almost a couple of dozens of parameters, which seems to be, we don't know where they come from. And but in spite of this ugliness, in the eyes, at least of some people, it turned out to be right. It's half a century that turned out to be right, and all the great ideas that people have come out to make it better has turned out to be wrong. The last one was supersymmetry, turned out to be wrong. So that's what we know. That's it. Okay, everything else you hear from us physicists don't believe it. Duality, holography, ADF, CFT, me talking about loop quantum gravity. These are attempts. These are not things we know about the universe. These are, grasping in the dark and trying to see a little bit ahead. Some will turn out to be right, maybe. Some will turn out to be wrong, for sure. We don't know. I have a lot of I have little confidence that a lot of things which are fashionable today will survive in the future. But the future will say. But it's important to keep this distinction clear. Good. So that's background, and you'll see how it comes in. What is absolutely spectacular is that these three pieces of information about the world seem to be able, at least in principle, to account with almost everything we see. Not in the sense that we can compute stuff out of that. We cannot. We need chemistry, we need biology, we need, and then we need engineering to make things work, of course, and the architecture for making our life decent. But there's nothing that seems to escape and to contradict these theories. So one might think that after all, everything obeys this theory. If there's one thing which seems to be a bit harder to fit there, it's a more mysterious than the rest, is dark matter. Astronomers have found this evidence for something out there, and there aren't many ideas, and I'll come back to dark matter. There aren't many ideas of what could it be. Maybe something not described by the standard model, maybe some modification of GR, maybe, but it's not clear. All right, so that's background, and now follow me in the trip. And the trip I want to take you with me, it's inside a black hole. I want to take you with me inside a black hole. It's an imaginary trip, of course. We haven't the technology, but to a large extent, it's what we are very confident, and I'm talking about physics that we rely upon. We have no reason to doubt that it is going to happen if we could go inside a black hole. If we were a bit more reach and a little more technology, we could do that. So let's imagine that we enter together in a starship, all you guys and Michelle and me, and we go toward a black hole. I mean, it's going to be long because the small black holes, just a few light years from now, but still, whatever technology takes time. And but let's go to a big black hole. There's a huge one in the center of the galaxy. We have enormous evidence today that black holes are out there, or at least that out there are plenty, millions, billions of things which are, at best we understand, well described by black holes. We take our starship and we go there. And I will first tell you what is a black hole, how would we experience that, and then go inside. So we get close to the black hole in the starship, and the first thing we notice outside the black hole is the following. Say we have got news from Earth regularly during our trip. Every day we listen to the news from CNN every day, or Fox News, or Al Jazeera, or China Daily, whatever you prefer. And we tune in to listen the daily news, which are sent from Earth once a day. Well, what's going to happen is that apart from the distortions, we're going to get this news faster than once a day. So when we get closer to the black hole, we get this news once every 20 hours, every 10 hours, every 2 hours, every 30 minutes. So very rapidly, we see what's going to happen in the future on Earth. Okay? This is a phenomenon which is predicted by general relativity. We're completely confident that this is the case. There are versions of this phenomenon that can be checked in the laboratory. So it's something we know about the universe. So if you want to know what's going to happen, 100 years in the future, is very easy. You just go near to black hole, stay outside, and you go sufficiently close.
We have a question.
Yes.
So Carlo, you're talking about an accelerated observer hovering outside the black hole, or an inertial observer falling into the black hole?
Same, doesn't matter. Both. I'm talking about a starship, which is still outside the black hole. It might be just free falling, but it's be convenient to turn the engine on and to keep yourself outside the black hole, waiting there. And while waiting there, we receive news faster and faster and faster. Okay. That's, keep this in mind. Now, also, the important thing is that in the starship, if there's no engine, we are free falling. But if we turn on the engine, we keep a distance from the black hole. Inside the starship, nothing is strange. Okay, times goes. You wake up in the morning, 24 hours to 24 hours. You brush your teeth in the morning. Time is normal. What is not normal is that you receive news from the Earth faster and faster. And of course, if you're smart enough, you can guess it by yourself. If we send news to Earth every day, every 24 hours for us, we send our news to the Earth, our friends in the Earth are going to receive this news at longer and longer time intervals. So every 24 hours, 25 hours, 2 days, 3 days, once a week, once a year. So if they have super powerful telescope that can look at us, they see us slowing down, slower and slower and slower. They see us sort of moving very, very slowly like that. And the more we get close to the black hole, the more it's slow. That is a distortion of time due to general relativity, which is, as I said, is measured. The other thing we might notice outside is a distortion of space in the following sense. Imagine that we have our engine, so we're keeping outside the black hole. The black hole is sort of a sphere. We're a little outside, and we can measure. We can go around and we can measure the area of a sphere around the black hole, certain number of, I don't know, square kilometers or whatever, and then we move in closer to the black hole and we measure another sphere. Okay. And of course, if you know geometry, if you know the area of a sphere, and then you move 1 meter in, you know the area of the smaller sphere. But to our surprise, the smaller sphere is not as small as we expected. So if you move 1 meter inside, the spheres don't become small as you would expect. This is not surprising if you think of two-dimensional geometry, right? If you think of a funnel is a circle. The inside circle is more far away than the outside circle. There's more distance between circles than what would you expect on flat space. So the same thing happens in three dimensions. A funnel is a distortion of a two-dimensional flat geometry. This is a distortion of three-dimensional flat geometry. All right. The other thing we notice, of course, you might imagine, is that the closest we are to the actual sphere of the horizon, what we call the horizon, to the black hole, the more our engine has to be powerful to keep us out. And if we go very, very close, the engine must be increasingly powerful. And we soon realize that to stay exactly at the horizon, our engine should be infinitely powerful. So at some point, whatever is the power of our engine, if we go too close, we can't resist anymore, and we start falling. So we're very courageous, no problem, we go in. Now we pass the horizon. Now we're inside the black hole. And what happens? We're nothing special. It's exactly like before. We keep receiving messages from the Earth, right? We keep seeing the star outside. It's anything. We know the theory well that now, unfortunately, if we send message to Earth, they're not going to get to the Earth. You know, remember, when we were very outside, very close, they were taking longer and longer and longer. Now they're not going to get there anymore. Well, whatever. Bye-bye, Earth. We'll see. Maybe we'll get there later. So we go in, and now the geometry, you know, this funnel geometry that we see, it's much more distorted. So we are in a sort of very long funnel, very, very long, a tube. Imagine a very, very long tube, extremely long. So inside the black hole, the volume is enormous. There's a much more volume than what would you expect from the outside. A black hole is a little bit like, you know, these fairy tales in which you go in the forest and there's a little hut and you go inside the hut and there are huge holes and gardens and all sorts of stuff inside. Well, that's what the black hole is. There's an enormous space inside. It's a volume that can be computed. It's not infinite, but it's longer if it's bigger if the black hole is old. Okay, so now we're inside, and it's normal, except there's all this distortion of geometry. There's this huge volume down there, and something strange, something powerful is going to happen, which is what the physicists call the singularity. The general relativity predicts that something very funny is going to happen, but careful, because if you read a common account, and if you talk with many physicists, you have the idea that what's going to happen is down there at the bottom, in the sort of the center of this. That's completely false. It's not true. What's going to happen is not somewhere. It's at some time. It's in the future. Wherever you are in this inside, after a while, the spheres around you are going to get squeezing you more and more. So this tube is going to be longer with time and more squeezed, okay? Until, now, reasonably, since we're engineering here, I should say until there's nothing to do, it's just too small for us to survive, too squeezed for us to survive. The curvature of this distortion of space-time is too large. But imagine, now it's really fantasy, but not contradicting laws of physics, imagine we could survive, okay? General relativity tell us that the heaven is falling on our head. I mean, we're being squeezed wherever we go. We're being squeezed inside this thing, becoming narrower and narrower around us. We can, you know, try to stretch in this long thing, but it's... What happened next? Well, everything I've said so far is predicted by general relativity. General relativity is reliable. So it's credible. I'm ready to bet all the money I have in the bank that which I've said so far, it's true. But general relativity is not reliable when this stretching, this curvature becomes too high. And this is pretty obvious. In fact, Einstein wrote the first version of his theory in 1915, and in 1916, he wrote a paper saying, of course, my theory is not the end of the story because it disregards quantum mechanics. So at that point, general relativity is not reliable anymore, and we need quantum mechanics. So we need to know what happened to gravity, space, and time in a situation in which quantum mechanics cannot be disregarded anymore. And for this, we need a quantum theory of gravity. And that's why I'm interested in this, because all my life, I studied a quantum theory of gravity. And it's not true that we don't have quantum theory of gravities. We have quantum theories of gravities that they're not tested. They're tentative hypothetical theories. And the theory on which I've been working, which is loop quantum gravity, it's a theory that it's a quantum theory of gravity. It's exactly something that can be used for computing what happened next. Now, loop quantum gravity it's precisely formulated for doing this kind of calculations. It's not a unified theory of everything. It doesn't try to solve the problem of standard model. It doesn't tell you, it's not the final theory of the universe. It's not the theory of everything, nothing like that. It's just a theory that tells you what happened when gravity cannot be disregarded, the quantum mechanics cannot be disregarded. Like there, when the black hole, in the moment in which the black hole falls around you. So you do the calculation, and the calculation is not horrendously hard in some drastic approximation, and has been done. To do it a little bit well, it becomes more and more complicated. It's been computed analytically, numerically, because there are some complicated integrals and so on and so forth. But it tells us something, tells us what's going to happen. And what's going to happen, it's not too hard to imagine. So let me tell you what loop quantum gravity suggests is going to happen at that point. And careful, I've changed the register here. It's not theories which are totally reliable. It's an attempt to understand what happened if you take general relativity and quantum mechanics and you make them work together. Within this theory, which is a coherent, conceptually well-defined theory, which is loop quantum gravity. Now, what's going to happen is tunneling. Tunneling is a phenomenon, is a typical quantum phenomenon, very well understood in elementary quantum mechanics. And tunneling is when you have a wall, and classically a particle could not go the other side of the wall, but quantum mechanically it could, like if there was a little tunnel in between. So it's a phenomenon for which you can go from one solution, one classical solution to another classical solution, which classically you could not, but there's a little probability of jumping from one to the other in quantum mechanics. And there is a standard way of computing these things. And the interesting thing is that in between, in the jump, a particle that goes the other side of the wall is sort of, you cannot think about it, it's a particle. It's really, you really have to think there's a quantum jump. It's quantum mechanics is about. So it computes probabilities of what's going to happen without telling you what happened in between. So here, I'm not talking about us being quantum there. I'm talking about space-time. The black hole is a structure of space-time, distortion of space, distortion of time. So what's going to happen to space-time in the moment in which we're inside, the things are shrinking around us? It's a quantum jump in which space-time itself, or if you want, space itself, jumps to another solution, okay? And where does it jump to? The calculation indicates that there's one precise possibility that, under some conditions, I'll come back to that, you jump into another solution of Einstein equations. So in another well-defined solution of Einstein equations. And it's very easy to think intuitively what's going to happen. The first part of the story was falling into the black hole. The black hole itself is matter that has been collapsing and is falling in itself. It's space-time itself which is falling toward a singularity. Now, if you have something falling and it hits the bottom, what happens in general? Take a ball, a football, soccer ball, and you throw it down, it hits the ground and bounces back, okay? Bouncing back, imagine a ball bouncing up. Bouncing back bouncing up is the same trajectory that going down, but sort of reversed in time. If you film a falling and then you project the movie backward, you see something going up. So imagine you film a black hole formation and everything of a black hole, and then you project the movie backward. What you obtain is another solution of Einstein equations, which is not a sphere where something can fall in, but it's a sphere from which something can come out. And this is well known since decades, and it's called a white hole. Now, people don't know if there are white holes in the universe, but people didn't know if there were black holes in the universe. So it might well be that there are white holes in the universe which are born exactly in that way. I mean, your black holes fall in, a star collapses from a black hole. There's a sort of compression and then a jump and then a bounce, and then you come out. And all this is perfectly well described by classical general relativity, except the bounce itself. So the black hole and the white hole were described by GR consistent with the outside. The bounce itself, it's where GR goes wrong. And that's where loop quantum gravity predicts that the bounce can happen. So now we have a white hole. Now, what is a white hole? It's just like black hole, except that backward in time. So if you're there, you just move out. You move out, you come out of the horizon, and you're home. So you said bye-bye Earth, but no, you can go back to Earth. You can go back to Earth. Okay, that was hard. It was scaring to go in. And of course, that's not realistic anymore because going through this quantum bounce has been squeezed to a very small scale. But still, you can go up, back to Earth. Except, remember the time dilation. So you can put numbers now and take a black hole of the size of the black holes that we see in the universe and put numbers. And you compute, well, the time to arrive there, it depends where the black hole is. Then you cross the horizon, you go in. How long does it take to get to the squeezing? For the big black holes, like the one in the center of the galaxy, if you put numbers, it's a matter of minutes, maximum day. So it's a very short time, say minutes. You go to the tunnel, you tunnel the other side, and then in a matter of minutes or hours, you come out the other side. But time, it depends where you look at it. Clocks do a different speed in general relativity, right? So now you can compute when you come out how much time has passed on Earth. And not surprising, you get billions of years. So you go in very fast, you come out billions of years in the future. You come out from the same location, from the same thing. Go in, and for you is just a little bit time later, short time later. From the outside, billion of years passed. So from this perspective, a black hole, it's really a star that falls into itself, becomes very compressed, bounces back, except that you're sort of looking at it enormously in slow motion. Okay? Most of this is classical GR, except the bounce itself, which is a quantum phenomenon. I believe that other quantum theory should predict the same thing, that other quantum theory of gravity should predict the same thing, but loop quantum gravity is the only one where you can do this calculation. You have a framework for doing this kind of stuff. So here's the full story. Black hole forms. You can go in, you come out, becomes a white hole. Everything which is inside slowly comes out, which, by the way, solves the so-called information puzzle of the black holes. How do you lose information of black hole? Black hole information comes in and bounces outside. I think the information puzzle is a fake puzzle that comes only if you believe in certain assumptions like holography, which are assumptions, are not something convincing, in my opinion. Now, I have to get to the detector. I've not yet there. How am I doing this time? Oh, I'm doing well this time. I gave you a picture of what's going to happen to a black hole in the distant future. At some point, it becomes a white hole. What is the jump in probability? Because the probability of a jump, this tunneling, is a probabilistic effect. So like everything in quantum mechanics, it might happen or not happen in any moment. So when is it that happens? Well, we have loop quantum gravity. We can calculate from the outside. If you're in, that's the only thing can happen. But if you're outside, what's the probability for this to happen? Which is telling you how long you have to wait before the black hole becomes a white hole. It's a quantum phenomenon, which is probabilistic. You do the calculation, and you discover that for a macroscopic black hole, the time is colossal, immense. So much longer than the life of the universe. And so that doesn't seem to be part of our universe. Seems just, the theory itself seems to say that that's not something we may expect. But there's one missing piece in the story here. As you probably have heard, it's a famous thing, Stephen Hawking became famous. In fact, his major result is a calculation where he showed that black holes actually are not eternal. If you have a black hole there, There's another quantum phenomenon, nothing related to the tunneling I mentioned, for which the black hole emits radiation. It's hot. It's called Hawking radiation. And this radiation can be computed, and but it loses energy, it loses mass, and it becomes small. So it becomes smaller and smaller and smaller. So given the mass, we know how time, with Hawking theory, we can compute how much time the black hole needs to become smaller, and very, very small. Now, the probability for this jump seen from the outside increases when the black hole becomes small. And when the black hole is very small, it's become very quantum, and the probability becomes very high. So now we have a scenario. Black hole is formed by a collapsing star in the early universe. We don't know. We don't know how a black hole forms. We see many, the big, huge quantum black hole, the center of galaxies. Nobody has idea today how they were formed. Black holes are very new stuff. They're big, small, all sorts. We're still learning about them. So black hole forms, it becomes small. When it becomes very teeny, then it can do the jump. But careful, very teeny black hole does not mean that the inside is small. Remember the hat in the forest, the small hat with the big thing inside. That's what the black hole here is. And the same for the white hole. So when the black hole is very, very teeny, the horizon is very teeny, the surface is very teeny. It may jump into a white hole, which is a teeny throat, but a huge inside. It's like a bottle with a small throat, but a huge bottle inside, very, very large. And then a black hole grows with time, a white hole decreases with time, and slowly everything comes out. So now we have a picture. Is everything we said before, but the white hole is small. The white hole is small because you have to wait for the black hole to evaporate to create one of them. How small? Well, we have low quantum gravity. You can compute how small, because the low quantum gravity shows that a white hole, the throat of a white hole, it's quantized, like the orbits of the electron around an atom. There's a quantization of area. That's the main result of loop quantum gravity. So the area can be zero, there's no black hole, or there can be a minimum area, or it can be bigger area. But if it's a bigger area, it can Hawking radiate and become small. So this is going to sit on the minimal area, which can be computed. And the minimal area is a Planck area. It's very, very teeny. Inside is big white hole. It's very teeny. And the mass is a Planck mass. Okay? Now, how much is the Planck mass? Planck mass is the natural mass for a quantum gravity phenomenon. Now, the interesting thing, the Planck mass is not small, nor big. It's a fraction of a microgram. A microgram is, it's my hair. The weight, the mass of my hair, it's a Planck mass. A little piece of my hair, a couple of millimeters of my hair at Planck mass. So from the point of view of an astronomer, of an engineer, is very small. From the point, depending which engineering, for engineering in electronics is not small. From the point of view of particle physics, is very large, because particles are in that accelerator are much smaller than that. This is this intermediate range. So now is the prediction. Imagine that. Oops, I lost you. Oh, here you are. Imagine that.
Now it's lost. Now we're lost.
Okay, sorry, it disappeared and appeared on my screen. I don't know what. Imagine that in the early universe, a lot of black holes formed, whatever size, when the universe was very, very hot, and they all had gone through this process. So now we should expect, if this is correct, that there might be a lot of little things with a Planck mass, like hair, all over the universe, and this will interact gravitationally, have a mass, but they're very teeny and do not have a charge. So they don't interact with light. You cannot see them. They're dark, but it's matter, and it's all over the universe. Okay? And now you say, wait a moment, the astronomers see exactly that thing, a lot of dark matter all over the universe. So the many if here. If a lot of black holes were produced in the early universe, now there are these remnants, these white holes floating around, and maybe the astronomers have seen them. Remember that black holes, nobody believed black holes, but the astronomer had seen the big black hole at the center of the galaxy in the 30s. The radio waves, the radio signal of the black hole at the center of the galaxy was captured in the 30s. It was very famous at the time. It went to the New York Times. The first time somebody put a radio antenna pointing to the sky, it got this strange signal from Sagittarius. Nobody knew what it is. For half a century, we didn't know what it is. Now we know it's a black hole. So black hole was detected before realizing that they were black hole. Maybe dark matter is white hole, already detected without realizing the white hole. So this is a possibility. So I was very excited by this possibility. So the natural thing to do is, how do we test it? Well, can we detect one of these little things, this hair flying through? The solar system is moving with the galaxy. Dark matter, we know how much dark matter there is. We don't know what it is, but we know how dark matter there is. So we can compute how many of these things are flying by. And, in a room like this, or like yours, every once in a while, not often, there's one of these things flying by, if this story is right. So how do we detect them? We cannot see them. We cannot have an electromagnetic phenomenon picking up. We need to pick it gravity. Now there's some technology for very fine detection. It's growing, and there is a technique that uses quantum mechanics. The quantum mechanics is a tool for detectors, which might pick this up. And that's my paper, my physical review paper that I published last week. In a word, you have a quantum particle, you quantum split, and if a white hole flies by, it pushes and pulls one of the parts just a little bit, so it goes out of phase with the other, and when you bring it together, you can do quantum interference. And the idea is that this can be done explicitly with Josephson junctions, which is a sort of splitting electron. So when one thing flies by, there's a little current that goes through, and if you have a lot of this, you might detect these things. Now, I don't know if this is how close is the technology for doing that. I'm not an experimentalist. I hope experimentalists are going to that. So if this thing is detected, it will be fabulous, because it will be a explanation of what is dark matter. This is a tentative. This is an idea. It's a nice explanation because it doesn't require anything else. It doesn't require new particles, new fields, modification of the Einstein equation. It just requires generativity quantum mechanics. So dark matter, if this is correct, is just, holes in space which are coming out. And it would be an indirect verification of quantum gravity, a theory of loop quantum gravity. How confident I am that this is the case? Well, I strongly hope, because it would be great, but I don't know. I believe it strongly on Monday. I don't believe it on Tuesday, Wednesday, I'm not sure, and so on and so forth. What is interesting in this story, I think, is that the possibility of bringing together quantum mechanics and general relativity, it's testable. It might lead in this way or in another to give testable prediction. We do have a theory of quantum gravity. Even without that, we have a obviously growing understanding of the world. We didn't know about black holes. We have a confused theoretical understanding of black hole long ago. So the story I told you, perhaps the most spectacular part is the solid part of it, how much the actual universe allows colossal distortion in space and time in ways that we control with classical general relativity, and how much a little bit of addition, like quantum gravity, might lead to better understanding of open questions, like what happened when you fall into a black hole. Without quantum gravity, you can just say, we see matter fall into a black hole, we have no idea what happened to it. Possibly a tentative explanation of dark matter and a way of testing it. Good. So I've talked for over 40 minutes. I would stop there and feel free to ask any questions about the scenario, about what we know, about what we don't know, about black holes, about loop quantum gravity, whatever you want.
Great, we'll take questions. So, yes, please.
Let me turn just 1 second.
Put the light on. Yes, it's on. We can't hear you right now. We're not hearing you. Did you mute yourself some? Oh, unmute maybe. Okay.
Thank you. Let me turn one of the two off.
All right, we're gonna start questions.
No, just 1 more second. I have to mute one.
Okay, testing.
111.
Yep, we hear you.
I think he just said.
Sorry for this confusion.
Yes.
No, something is wrong. Let me do this. Wait a moment. Wait a moment. Let me do this. Use the other one.
It's gonna get worse.
This works,
Yeah.
I think. This works, yeah.
Yeah.
Okay.
You have a question just after her, take a seat and we'll take all your questions.
Can you hear us?
Yeah, now it's fine. Sorry.
Go ahead.
Your explanation for white holes also later on drew in like Hawking radiation, and the whole, at least the way I heard it, Hawking radiation was the like antithesis to white holes because the information's preserved in the process, so there's no need for the energy to go or the output of a white hole. So how's that not violating the third law of thermodynamics, and also it's trying to impose a symmetry that why are you trying to impose that?
What's the last thing you said?
Like that's trying to impose a symmetry onto black holes, that why are you assuming that?
Which symmetry?
It's just like the black holes into white holes process. Yeah.
What? So the question is,
Dynamics with Hawking, and then why is he adding and trying to make black holes like symmetric in that direction?
why? Because you can. Or you think you
Okay.
can.
In that case, then the explanation for dark matter, your justification was that it matches the observed results. Does it predict anything different? Because otherwise, isn't it just a different theory that could not be proven?
Good. I mean, there are two different questions here. Let me start with the last one, and then address the first one. That's why we need a detector. If we see that these things exist, these Planck scale particles, then we have direct evidence that these are the dark matter candidates, right? If we see them, we can count them and see how many they are, and then we have solved the problem entirely. Until we haven't seen them, we don't know. It's just an hypothesis like the others. What is going on with dark matter is that there are various detectors for various kind of things, and for the moment, the detectors which have been built haven't seen anything. The first hypothesis for a while was a supersymmetric particle, and the detector that were built to find those things haven't seen anything. Now, your other question was about the thermodynamics, the third law of thermodynamics. Did I get right?
Chime in about this question, just like so the what's the density if all the whole dark matter is or Planck scale black holes? What's the density of them? How many of them are, you know, per cubic meter out there? How many of them are like zipping through, or, you know, our classroom just right now?
One every few months, your classroom.
Right. I see. So
The density is it's not very high, but we are moving fast in the with dark matter is expected to be not rotating in the galaxy while we rotate. So we have there's this cloud that we are moving fast through the cloud, which brings up a little bit the number of particles that go through us in some time.
yeah, and then okay, great. And so but the plan is to do this in the laboratory, right?
Yeah.
That is, you put these detectors, and you have a signature for seeing when a black hole,
Yeah.
a Planck scale black hole goes through your detector. Okay, cool. I'm definitely going to. I haven't seen this. Just came out, this PRL.
Yeah, it just came out, yes. And of course, you know the direction we're supposed to come from, right? Because we know which direction the solar system is flying with respect to the non-rotating frame.
Right. Actually, maybe I can add to the first part of your question.
Yeah, let's go to the first part of the question because I want to get it better.
That which is when I was studying with Stephen Hawking in 1984, and at that point, he believed that because of Hawking radiation, that black holes and white holes were the same thing. That
Oh, really?
yeah. I don't know. I was wondering if you knew.
Oh, no, wait. I didn't know that. Is that written somewhere?
Good question. I don't know. I mean, he would claim it. I mean,
Oh, because look, Seth, listen,
he would.
I,
Right,
I,
he would say like,
no, because I've been simplifying.
Black holes are white holes, you know.
But they are. That's exactly what the theory says. I've been simplifying a little bit the story. When at the end of the Hawking evaporation, white hole, macroscopic white hole is unstable. This is well known in GR. It's unstable toward something that can happen. It can very easily transform into a black hole. So if you have a white hole and you send some matter very near to here, it becomes a black hole. Okay. And then when the black hole starts radiating again, it becomes smaller and smaller and smaller. Now, the point is that when it becomes Planck scale, the probability that as a white hole becomes black hole and the probability as a black hole tunnels back into white hole compensate. So at the end of the day, the quantum mechanics stabilizes the small white hole by making them black and white at the same time. It's like you have a quantum two systems. You go down to the minimum of energy, which is a superposition of the two. So I didn't want to go into these details because they're tricky, but the actual theory of these Planck scale things is that they're quantum superposition of black and white.
Like Barack Obama. I don't want to say that.
And what was it? The thermodynamical question about? Should I say a little bit about what happened to information?
Yeah, I was wondering, do you have the quantum superposition of black and white formulated in terms of loop quantum gravity? Do you have
Yes.
the mathematical formulation of that? Is that something we could read about?
Yes, but yes. I mean that part is it's not Yes, it's not the first principle thing, right? It's when you start applying the theory, you use all sorts of drastic approximations.
Right.
Um, but
makes
yes, you have a paper on the stability of the remnants.
Factor that you were describing in your paper, is it just sensitivity or also the design of it?
It's the design of the paper as done by a theoretical physicist who's never entered in a lab in his life. So the engineering here are gonna laugh if they read what I've done. But it's the paper is a theoretical part, just split the particle and see, and then a slightly better part in which we actually try to do concretely this, and that's a Josephson junction idea. You pile a lot of this, and essentially it becomes a detector, a very super sensitive detector of little forces. But that's the paper just come out. You need somebody who knows about detectors to look into that, not me.
Also, Hawking's views on white holes and black holes are in Strominger's online lectures.
Yes, actually, Strominger, these people had a similar idea of thinking of remnants of small things with a big inside. And then abandoned in the 80s, ideas like that, but then they abandoned them because they never thought of connecting to white holes. And they didn't have the quantum theory that we have now, many decades later, to make a little bit more concrete those speculations. They abandoned because they thought that there were certain problems, but I don't think these problems are there.
Hi, Dr. Rovelli. I'll preface this just by saying that
Hi.
I'm not a student of this class, so I really don't know what's going on. But a couple summers ago, I read your book, Reality is Not as It Seems. I was a huge fan. I really like the idea that you can get excited enough about this thing that you get pulled over for driving too fast, just thinking about it. Whereas a lot of people, I guess, adjacent to your field can be very morose about this kind of stuff. But I was just curious about the properties of black holes versus white holes. I didn't quite understand what sets them apart. So you have kind of this Harry Potter-esque property where you have like the mansion inside of the top hat, right? You reach in and it's a much, much larger space than you would expect from looking at the outside. And then also, as I understand it, as you get to the event horizon, right, as you're transmitting information out, you go from, okay, it takes 10 years to 100 years to effectively forever. No information can escape. In a white hole, then, when I cross the event horizon, do I see the opposite geometric property? Do I go into a space that's even smaller than I anticipated? Or how do I get the inverse properties, I suppose? What characterizes a white hole's behavior?
Some of the properties of black hole and white hole are counterintuitive, and the key counterintuitive aspect is that seen from the outside, a black hole is just a sphere, and everything outside is static. Nothing changes. A white hole also is a sphere. Everything outside is static and nothing changes. Okay. In fact, everything outside is the same. You can be in orbit around the black hole, or you can be in orbit around a white hole. The force is always in the same direction. So they're very similar. And yet, this difference is that if you let yourself go toward a black hole, you cross the horizon and you are somewhere else, and you continue, and there is no trajectory that comes out from a black hole. Okay. Now, if you're outside, you might see something emerging from the black hole just because it was never inside. Imagine that the black hole was formed by a collapsing star, right? The star collapses, and a moment before entering the horizon, a guy there shoots something toward the outside very, very powerfully, and it stays out, but it takes a long time to come out. So if you look from the outside, the star comes in, the projectors stay here a long time, and then it comes out. Okay, so you might see something come out, but it's not really coming out. It was coming from the sun. Now, a white hole is completely reversed. So you cannot go in. You say, well, what do you mean you cannot go in? So if I let myself fall, what happens? If you let yourself fall, have the reverse of what you said before. So if you let yourself fall, you hit the whatever matter was coming out. Okay? So just take the picture that I gave you before and time reverse in your head. Make a movie and make it backward. That's possible. Okay? Now, obviously, in any movie in which there is some water falling into somewhere, if you do the movie contrary, you see the movie coming out, right? So for a white hole, you can have things coming out.
And how about the time distortion properties? How are those different for a white hole? How would I receive or transmit information as I approach one?
They're the same. The outside is really the same. So if you approach a white hole, it's the same as before. In fact, everything is the same, and that's the reason for which
Same as if it were just any other part of space, or the same for as if it were a black hole?
Same as a black hole. Same as a black hole. So that's the reason for which if you throw something against a black hole, sorry, if you throw something toward a white hole, I said it's going to stay there until it hits something that comes out. But maybe something has come out long time in the future. Yes, but if you're there, the long time in the future is very short for you. So you're there and boom, you get something taking you out. And if it's nothing, at some point, black holes form from nothing, white hole dissipate. So if nothing hits you, at some point, there's no white hole in it anymore. So look, when I started studying white hole, I spent weeks and weeks and weeks with my students saying, how the hell it works, this thing? So it takes time to make sense of them. And yet, it's just classical general relativity. So it's just reading out of the equation. There's no speculation here. It's all what the theory predicts. And general relativity, everything it has predicted has come out right. So I wouldn't doubt that this is possible. The only question is how white hole are produced. And so what originate them? But that's the same question of how black hole die. We don't know how black hole die. So it's very tempting to say, well, I know how white hole produced it, but by dying black holes. It's just, you can glue the two things you don't know, and quantum mechanics connect the two.
Very interesting stuff. Thank you.
Yeah, so Carlo, first of all, I will try to find this reference to Hawking thinking about this in 1984, because it was very striking at the time. And my recollection was that shortly afterwards he changed his mind. But it was never possible to tell why he changed his mind, because he would just tell you that he changed his mind. So
can I make a little comment here?
Yeah, please, yeah.
The scientist whose work I know who changed his mind more often is Albert Einstein.
Yeah. That's good. It's good to change your mind.
Yeah, absolutely.
Yeah, anyway, I think we will wrap up then if people don't have questions, but I want to thank you for the way you've explained it and always telling it like a story, and the lovely fairy tale version, particularly because part of what we do in this course is we write
I
stories
know,
on the
I know,
heart.
I read that. That was
Right,
that's
completely
why.
up our alley. So is your White Holes book, and but one of the assignments we've done is, you know, Kipling's Just So stories. So
Yeah.
tell a whimsical fable about the origin of the universe or one of your favorite physics principles. So yeah, it'll be fun to have a little more writing based on what you've spoken to us on
Yeah,
today.
fine.
Thank
Great.
you very much.
Wonderful.
Great, thank you.
Fantastic. Thank you very much. Thank you, Michelle. Thank you, Seth. Say hi, everybody. Bye-bye.